Hey guys, happy Monday. I'm sorry I can't be there today, but I wanted to record this video to give you guys a little bit more information about what you're supposed to be doing today. So hopefully this will kind of preemptively answer some questions that you might have about why you're going through stuff today. I wanted to show you where everything is, make sure you can easily access it. Hopefully you have headphones and you're not listening to this out loud in class and bothering everyone around you. So I know all of you have headphones, so hopefully you have some. If you don't have some, you can either, I guess, ask a friend to borrow some or ask them about the instructions if you're confused. So today you guys are going to be finishing the 1.4.3 packet that we started in class on Friday. In order to access the information for it, you go to Schoology. I've got my Schoology pulled up right here. You can't see all this stuff. You can just see interactions. And then we are in investigation 4. And this, I need to change the date on this because it will be Monday as well. So let's change the date. Monday, March 2nd. Cool. So Monday, March 2nd. So if you click on this, the first thing that's going to pop up in this folder is the Nearpod from the one we started on Friday. So you'll put in your information, you'll click join session. It'll work the same way. You can click through. You don't have to do the time to climb. Again, obviously it'll be the same. And I actually don't think it'll let you now that I'm looking at it. So not a problem anyway. All this we did on Friday. If you want to, I would recommend reading through the slides just to kind of as a refresher for what we did on Friday. I know you've had a whole weekend to forget. So go through, look at the slides. Refresh your memory, what the gold foil experiment was, what did Rutherford find, what was so important about it, why do we care? It's always an important one. Let's just skip ahead here. Yeah, we did the lab, the simulation. Okay, so how do objects become charged? So on the worksheet on Friday, every class stopped in a slightly different location. I tried to get through as much as I could with everybody. But I think most people got to the nuclear model part. So the part at the bottom that says, where is it? Nuclear model. So if you are not up to that point yet, take a minute, maybe pause the video, and you can go back. So on these Nearpod slides, you can go back to the simulation, finish it, do what you need to do to get that finished. So then once you're on to the nuclear model section, you're going to answer 8 and 9 using the information from all of the slides up to this point. So number 8 says, recall that Rutherford observed that 1 out of every 10,000 alpha particles bounced back. What does that tell you about the relative size of that small, dense, positive core, which is called the nucleus? So that's where we're getting a nuclear model of the atom. The nucleus is the small center. I'm trying to think of like a candy that has a small center, but I can't think of one at the moment. It's like the peanut, I guess, in the middle of an M&M, but peanuts are kind of huge, so that's a bad example. But small center is the nucleus. And what is this? If only 1 out of 10,000 actually hit that nucleus, what does that tell you about the size of that nucleus? I mean, we know that the positive is concentrated in a small area because the simulation taught us that. But exactly how small is it if only 1 out of 10,000 alpha particles actually hits it? So think about that for number 8. For number 9, and again, if you need to pause to answer these questions and then continue the video, or if you just want to watch everything straight through, it's up to you. Number 9, it says, why is it surprising that positively charged protons are packed together in a small space? So if we have a bunch of positively charged things, positively charged protons, that's what they're called, positively charged protons. I need like an actual proton. I have nothing. Yeah, whatever. You have a bunch of positively charged protons packed together in a really small area. Why is that wrong? Why does that seem wrong? What is it that you would naturally assume positive protons would do? if they were packed in a very small area together. So for number 9, think about that. What do protons do? Or better yet, what do just positive charges do when they're packed really closely together? So that's number 9. Number 10 is a section called One More Mystery. So we've got one more mystery to solve, not quite as exciting as the mystery box. By the way, here is, I should just make this full screen. Aw, but you lose my pretty face. No, I don't want to crop everything out. Here we go. So there's the nuclear model of the atom. This is what Rutherford came up with after his experiment. He's got this small positive center, so the nucleus, the small positive nucleus, and the electrons he decides are kind of floating around it. And that's the nuclear model of the atom. So the one more mystery to solve is all about the mass. So we talked about AMUs, atomic mass units, on Friday. It's how we weigh atoms. Excuse me. It's how we just describe how heavy they are. And the model that's suggested by Rutherford's experiments was kind of confusing, because why are these positive protons packed so closely together? They're supposed to repel each other. They're like charges repel. We've been talking about that since day one. That's like one of our fundamental rules, and yet we've got all these positive charges packing together in a small space. What the heck? So he kind of looked at hydrogen, because hydrogen is actually just one proton. Hydrogen is the smallest atom, and it's just because it's just one proton. And it makes sense, right? Hydrogen has a mass of 1, basically. If you look at it on your periodic table, hydrogen's got a mass of pretty close to 1. And yeah, right there. See? 1.008 is the mass of hydrogen. No, hydrogen. So that makes sense. It's got 1 proton. Remember we said that electrons basically weigh nothing. So the electron's not contributing anything. That 0.008 is not because of electrons. But why? What about other atoms? Hydrogen makes sense, but what about everything else? So we look at helium. Helium on the periodic table has a mass of about 4. And yet helium only has 2 protons. That's what this number up here means. The number on the periodic table that it is says how many protons it has. So beryllium has 4 protons. Iron has 26 protons. Arsenic has 33 protons. Platinum has 78 protons. So you can easily tell how many protons something has just by looking at it on the periodic table. But why is the weight different? We know electrons don't weigh anything. Protons weigh something. They weigh 1. We know they weigh 1 because hydrogen only has 1 proton and it weighs 1. So we know protons weigh 1. What else is giving these other elements such a higher weight? Why is helium weigh 4 when it only has 2 protons? That just doesn't make sense. What else is in there? What is helium hiding from us? Sneaky helium. So we would expect helium should only weigh 2, since it only has 2 protons, but it doesn't. It weighs 4. So we got to kind of figure out what else is going on in here. And the way that Rutherford and everybody else at the time kind of justified this was this idea that there's another particle in there. There's another smaller particle in there with the protons, with the electrons. And this one they called the neutron. Yes, this is the particle that Jimmy Neutron is named after. So the neutron is neutral, which makes sense. Doesn't have a charge. It's completely neutral. But it's still in there. And it has mass. It has the same exact weight as the proton. So if we've got helium with a mass of 4, that's saying that it's got 2 protons and it's got 2 neutrons. And the 2 protons and the 2 neutrons add up to give it a mass of 4. So that's why Rutherford says that's why these atoms have a greater weight than they have protons. So these he called neutrons. So this is another subatomic particle, another vocab word. That would be good to write down somewhere. Just a thought. And the neutrons also kind of help explain why protons would stay together in the nucleus, why these positive things would stay in the same space together even though they would naturally repel. So the neutrons, you can kind of think about them as like glue for the nucleus. They're also in the nucleus with the protons. They make everybody play nice. So whereas the protons would not normally like each other, the neutrons are there, it keeps everybody getting along, keeps everybody nice. So there's an open-ended question on here. How does the idea of the neutron help address the puzzles about why protons stick together? So if we kind of update our nuclear model of the atom to include these neutrons in here, you can see it makes more sense than why protons would be in the same space together if they're not directly next to each other. There's that kind of buffer in the middle. So you don't actually have to answer this question. It was just something for you to think about. But the neutrons basically are the buffer between all the protons. So, yeah, that's what I just said. There's another force that exists inside atoms. This is another good thing to know. It's called the strong nuclear force. Basically, this is a force that just exists between protons and neutrons in the nucleus. So it'd be like you've got electrical force between positives and negatives, and you've got magnetic force between north and south. This is a completely different force. It's a strong nuclear force between protons and neutrons. And it's about 100 times stronger than the electric force. So as much as those protons would love to push away from each other, the strong nuclear force is so much stronger that they can't do that. It's 100 times stronger. So maybe the protons do want to get away, but the strong nuclear force takes over and it holds them together. And it can only act over very short distances. So it's why the nucleus is so small, because that strong nuclear force, it has to all be close together. Okay, now we've got a new timeline. Woohoo! I know you guys love the timelines, because that means it's brochure time. So, if you are in 1-2, your brochures are in the very top shelf. If you're in 3-4, you guys are the middle shelf, and if you're in 5-6, you are the bottom shelf. So take a minute, maybe if you've been watching this and kind of pausing it as you go pause it and get your brochure out. Excuse me. And then we can add in the nuclear model. So here's my boy Ernest Rutherford. He is much more handsome than JJ, if I don't say so myself. JJ was like, he just looks mad. He's got the stronger stash going on. Little side swoop of the hair. But then we come to Ernie, and Ernie just looks a little more well groomed, in my opinion. So this is Ernie. And he does his gold foil experiment in 1911. So that's the important year to remember here. 1911 is when he does this. And that's when he creates this nuclear model of the atom. So in your brochures, what you're going to actually have, and I'm going to put a picture of this in Schoology in this folder, just at the bottom underneath the reading. Well, no, I'll probably put it in between the Nearpod and the reading since you're going to do this first. So that will be a picture of my brochure to show you what you need to do. But basically, it follows the same format we've been doing. So you're going to draw a picture of the model. Make sure you put those years and dates. So in this case, it's 1911. And then description of the gold foil experiment. So basically, how did this model come to be? Why did we jump from plum pudding to this? What was the reason for that? So that's what you need to have. I know a couple classes got around to this and a couple didn't, so kind of depending where you are. At the bottom of the page here where it says JJ and Ernie, JJ Thompson and Ernest Rutherford, you need to go to their Wikipedia pages, which you can click on just from the timeline. So here is Ernest's. You can go back and find JJ's too. Oh, look at that page.